And coming soon is also the application of such photodetectors as spectrometers with the aid of machine learning that controlling the operation of the photodetectors. And also we have a line of works in the polymer graphene doping. There we make photoresists and e-beam resists that dope 2D materials. We started with graphene in this work in 2018. Now we have, this was a positive tone resist. Now we make negative tone resists that dope to the semiconductors, tungsten selenide, molybdenum disulfide, and they can make them less p-type or convert them from p-type to n-type and so on. That is very exciting. And with that, I would like to thank my group and some of my collaborators. My interest is to find collaborations for multinational projects, mostly in the basic science of optoelectronics, and also for possibly for applications and engineering. Thank you very much.
Thank you, Doron. The good news is that Uriel Levy is here and can share with us his presentation. The bad news is...
What's the bad news?
The bad news is that we have to cut short the round table, but that's okay.
Okay. So let me start. I'll move to presentation mode. One sec. One second. Yeah. The settings should be.
You have to share first.
Yeah. Hang on. I will do sharing. Yeah, I hope that now you can see my presentation.
Yes.
So given the fact that I have 8 minutes, I've decided to focus on one specific work of ours. In general, we are active in field of nanophotonic devices with diverse materials from dielectric to plasmonics, waveguides, metasurfaces, photodetectors, modulators, but also quantum technologies and devices by integrating nanophotonic devices with atomic vapor like rubidium. So these are the main theme of the group, and it's quite diverse. You can take a look at the website. But today I'd like to talk to you about hyperbolic metamaterials and how we integrate them with 2D materials for enhancement of light emission. So let me start. Let's see. Yeah. So just a little bit about what are those hyperbolic metamaterials. In general, metamaterials, these are like sort of artificial sub-wavelength structure media. And the idea is that these media has properties that are not out there in nature. So these are some unusual optical properties in particular. You can control propagation of light and some other waves in these metamaterials. And maybe the claim to fame is that they can have also negative permittivity and also negative permeability, giving rise to negative refractive index, which is still a phenomena under debate. If we look at hyperbolic metamaterials, we can see the epsilon tensor. So it has epsilon x, epsilon y, and epsilon z. And in general, they can all be different from one another. And in particular, the idea with hyperbolic metamaterial is that you have one of the epsilons is negative and the other two, they are positive. So that's the idea. If you can have that, and you can have that, then new opportunities are arising, and let me show you how. So basically, these are the dispersion diagram. What you see here, these are the dispersion diagrams, and you can have elliptical isofrequency surface or spherical isofrequency surface depending on this epsilon. So if you can really have this case where, say, epsilon perpendicular is negative and the other one is positive, then you can have either elliptical or hyperbolic dispersion curve. And now this is what we see. So standard, if you just take the electric material, you have a sphere, okay? We know omega is proportional to K, and this is like a radius of a sphere. So this is in the, for a given omega, you have a surface. You have a surface with the shape of a sphere, of the shell of a sphere. So in that case, the K vectors are very limited, and the density of states is limited to the size of the sphere. But if you can have hyperbolic dispersion, then you have an hyperbola, which is more or less open, and then your density of states is so much higher compared to what is bounded here in the surface. So you can see that also in this cartoon over here on the right, where the lower bound state, these are the standard cavity modes of a dielectric. And as you move to the hyperbolic regime, then you can have your structure supports much higher K vectors, meaning that your density of states is so much higher. How can you get that? You can get that with some alternating layers of dielectric and metals. Okay, and these are the hyperbolic metamaterials. Okay, and these hyperbolic metamaterials can take all kinds of shapes. You can see from A to F, all kinds of ideas how to make those. Let me show you our work. What we do is not only we have hyperbolic metamaterials in 1D, we actually have it in 3-dimensional. So in 1 dimension, it's actually the alternating layer of silver and dielectric, in our case, like 6 alternating layers. And in the other 2 directions, we are patterning the structures as nano antennas. So we have confinement of light, which is very strong, and we still have the hyperbolic dispersion term. You can see some SEM images of this structure, and you can estimate the size by the scale bar, which is like 400 nanometer. So the period is about 400 nanometer. The height, the thickness of each layer is really few nanometers. This is the scale we are talking about. Okay, now let me show you our experiment and simulation results. First, we have analyzed the structure just to see the transmission through the structure. So we have the simulation result in kind of orange and the experimental results that's in blue. And for more or less, they match each other fairly well. Now the idea is to see what is scattering and what is absorption. So you can have enhancement of the states, but the question is, you are enhancing those states as radiative modes or as non-radiative mode, like quenching. So if you can have enhancement of your scattering, your radiative mode, then you can really enhance the emission of light. Unfortunately, typically in all these nanostructures, you enhance both. You enhance both the scattering and you enhance the non-radiative mode, and it happens at the same spectral location. What's so nice about those hyperbolic metamaterials that not only they provide enhancement, but they also provide a mechanism. I don't have the time to go into the physics, but they provide a mechanism to separate between the scattering and the absorption, separate by spectrum. So you can have a specific spectrum in which you are enhancing your scattering or radiative mode, but there is no much absorption. And that's why we can really enhance light emission from these structures. So that's the idea. You can see here, this is the simulation of the epsilon parallel and perpendicular. And there are 4 points like B, C, D, and E. And now you can see our measurements for scattering and absorption. And you see that as we go to longer wavelengths, the epsilon becomes more negative, give rise to significantly enhanced scattering, which is separated spectrally from the absorption. So this is really a great point to work in, the black point. Okay, that's a really nice place to work. The green one is also fairly nice. So now let me show you some more results. You can see here the flake. It's a WS2 flake, and you can see this flake on top of our on top of the glass and on top of the HMM cavity. And clearly you can tell the difference in light emission. You can see that the photoluminescence from the flake, which is on top of the HMM, the hyperbolic metamaterial, is so much larger. And in fact, we see enhancement of either 30-fold or 3,000-fold. What is the difference? The overall enhancement, like the engineering number that we measure, is enhancement of 30. But if you normalize to the area of the antenna and you ask what is the enhancement of an individual nano antenna, this is about 3,000. So physically it's 3,000. Engineering-wise, or like what kind of light we measure in a microscope, that's factor of 30 enhancement as compared to the material which is located on a bare glass. We have this, I don't have time for the simulation to explain all the modes, but there is explanation to that. Well, maybe just to say a few words, there are three mechanisms that are related to the enhancement. So first you enhance the excitation, and second, you enhance the emission, and third, you are also having a beaming effect, which helps you to collect more light. So instead of just radiating into 4 pi steradian, now it's really the radiation is beamed by the design of these antennas. So you have a fairly nice benefit. And we've also looked into the time domain and performed time resolved photoluminescence measurements to see that we have about 6-fold enhancement in the time response. There are 2 papers dealing with these results. The bottom one is about the structure with the WS2. The first paper is basically same concept, but different material, some quantum dots that are also engineered around the hyperbolic metamaterials. And these 2 papers, I think, summarize the results and the main ideas behind this concept. So I guess our time is short. Let me thank you for your time, and I can, oh, I forgot one more slide, sorry. We have done also Raman measurements, and we have seen enhancement in the
We have no
Raman.
time for the Raman measurement. I'm sorry.
Yeah, five-fold enhancement in the Raman, and also a little bit of a shift of 3 inverse centimeter, which means that the WS2 layer has some strain after we transfer it to the HMM nano antennas. So with that, basically, I'd like to conclude. We've demonstrated this large area enhancement of photoluminescence, and we are talking about number either 30 or 3,000. We have also seen some Raman enhancement, and we have also verified it by time resolved photoluminescence measurement. Thank you very much for your time, and sorry for showing up late for the event. Thank you.
I would like to thank all our speakers of this session, and open the room for discussions, questions from the participants, questions from the crowd.
E poi le diamo un po' a destra, un po' a sinistra come le riceviamo. Sì.
So let me ask a question, and it's not directed to anyone specifically, but I would like to ask all the speakers of this session, what do you think is the main challenge of characterizing nanomaterials? Okay, let me rephrase.
Maybe I can make a comment maybe on your question. So I would say if you look at the nanostructures, what we typically do, at least in my experiments, which are ultrafast spectroscopy, is we characterize an ensemble of nanostructures. And so we assume that what we derive are the average properties. Of course, if we could, some characterizations are possible in individual nanostructures. So for my technique for ultrafast spectroscopy, going to single nanostructures becomes really challenging, and this will be certainly an open challenge for the future to really be able to look at the individual nanostructures and see the distribution, the differences in the non-equilibrium response.
Can I ask a question?
Of course.
To all the participants, I've seen, you know, the materials we synthesize in my lab, we noticed when we do high resolution transmission electron microscopy that there are some specific types of defects, and we think that some of the properties may be related to this. For example, I mentioned about the copper sulfide that has a band gap that was something like 2.5 electron volt, but was more conductive than silicon or germanium, which have, as you know, much smaller band gap. What, besides HRTM, do you think there is no spectroscopy or other technique that can help to detect certain types of defects without going to the complication and the cumbersome way to do it with the HRTM? So it seems that the answer is no.
Well, I guess it depends on your material. Some defects are phonon sensitives. Some defects are electron sensitive.
So for example, let's say vacancies, excess of vacancies, or twin boundaries, or things of this kind. Is there any way to detect them with some non-microscopy technique? Okay, I think I got the answer.
I think you got a pretty good. I think you got a pretty important subject here, though. Most of the time, the characteristics are very defect dependent, and if we can't characterize the defect properly, then we don't know if we characterize the theoretical material or the let's call it the real one. And I was wondering if there's any way to correlate to that, other than measuring differently the defects and the characteristics.
I would have a comment. So it's gonna be very sharp, but you know, usually when you have this kind of very nice forum and conference, it's very interesting and we have a lot of contact, but we don't have something concrete at the end of the day. So could we have now, we have the embassy of Italy, could we think about something that exists with other countries like the French embassy, that you have some French scientists that could be that could come to Israel for a period of 1 to 2 years. So it's called Chateaubriand from one direction to the other, so that we promote the collaboration between the two countries. And on the other side, could we also lobby the topic of nanotechnology, nanomaterials, to maybe the Ministry of Science in Italy, in Israel, when we'll have a budget, of course, but I guess it's the same in Italy. I'm not sure that you're better than us in politics. But I think that we should think about moving forward now that we have the playground. So I don't know if someone from the embassy is here. I guess so. Yes. Stefano?
Yes, I am here, but I just missed your question because I was doing something else. Can you repeat, please?
Yeah, sure. I was thinking about some funding in the way that is for other embassies. I'm French, so I very well know what's going on with the French embassy, where you have some, it's called volunteers, that could do a period. There are scientists that could do a period in Israel, or to get a fellowship for Israeli people going to France. So could you think about such a scheme from the Italian embassy?
Can I, David, if I may, Stefano, I want just to, before maybe Stefano answers, there are things like Erasmus mobility grants. They're not for 2 years, but they allow faculty to go for a certain amount of time.
There are many options.
We have many of them. The question now, you're asking for something much longer term. So now, Stefano, the floor is yours if there is something for a year or two. But
no, at present we don't have in the frame of the bilateral agreement. We don't have any scheme for visits of I won't say for 1 year, but neither for a few months. So there is only one possibility, but it's one scientist per year. And the possibility, the so-called Rita Levi-Montalcini fellowship. So one scientist going to from Israel to Italy for 4 months, and another scientist going from Italy to Israel for 4 months. And as usual, Italy fixes a particular theme or particular field of research for every year for the selection of the scientist, while Israel up to now has left open the field of research, but it's just one per part. So it's not really, it's not a flexible scheme. We have yes, Italy has other bilateral agreements with other countries that which foresee also the exchange of scientists and students, but in this case we don't have with Israel. You have to pass through the bilateral projects. Erasmus is a possibility, of course, but then you need to enter in a project in a Erasmus consortium, which usually includes only a limited number of universities, so it's not nationwide. So if your university is a partner in an Erasmus consortium with another university in Italy, and then you can set up exchanges of staff, exchanges of students, exchanges of researchers, but you have to be in the same program, in the same project, in the same consortium. So it's not so flexible, I would say. We tried a couple of years ago, we tried to have a limited budget to give grants for short visits, like a few weeks. But it seems that both ministries in Italy and in Israel are not so keen to use this tool, because they say that it's too complicated. They have to evaluate the applications several times per year. And so up to now, the answer was no. I'm sorry, because I feel that this would be very important and very useful. And also the previous scientific attaché, maybe someone of you has met him, Stefano Borcaletti, had the same idea, but we didn't succeed. We will try again. I'm sorry.
But the Erasmus mobilities are interesting vehicles now that they were mentioned. And in fact, at Bar-Ilan, we have quite a few of them with many universities, University of Bergamo, Politecnico di Milano, University of Padova, now University of Brescia. And they allow students to go there for something like 6 months, more than one in every Erasmus, and the faculty for a few weeks to go and teach courses. In fact, the frustration we have right now at Bar-Ilan is we have quite a few of them and we don't know how to use the money because we cannot catch the plane. So, but David, on the practical side, I want to build on what you just said. So, I mean, I've been doing this on an individual basis. I was absolutely fascinated by all the presentations, and the quality of the presentation, the quality of the research was absolutely impressive today. And, you know, some didn't relate much to my field in terms of collaboration, and some did. So what I did, I took notes of which ones I thought that maybe there is an avenue, and contacted some of you and said, you know what, can we talk? And I think I suggest all of you to do the same. So you have seen a lot of interesting things, and some of them you can think based on their presentation of what could be joint synergies between you. And I think really the action is what we call the after sales, not the sales, the after sales maintenance. So now to contact each other and see, okay, let's do a Zoom together. Now it's easy, we don't have to travel. We just push the Zoom on, and then we see what each other does without the limit of the 8 minutes or 10 minutes like we had today. And then see if there is something that can be done. And that's how it usually starts. I think at this point, unless there are questions from either the attendees or the panelists, I think we can successfully close this workshop. Stefano, is there anything that needs to be said from the embassy side?
Yes, I'll say that I was very, very positively impressed from the level. I was not able to participate in the full meeting, but I was present for a while at the beginning and now also, and I've been really impressed from the level of the contributions for the number of the participants. So I think that from my point of view, this has been a successful meeting, and I really hope it will be the first of a series of future meetings and other possibilities, either organized with the help of the embassy and also by yourself. You surely you will get a lot of opportunities to meet and to work together. I just received a message from the ambassador. He's saying that he unfortunately cannot connect because he is completely taken by the preparation of the arrival of the minister, and says that he also is very happy about the success of the meeting. I sent him some news during the day, and so. I thank you, all of you, for your participation, for your commitment to the success of this meeting, and in particular Gilbert for having organized and followed all the work in these past months. And I hope to see all of you again in person and to shake your hands and to have a nice dinner with all of you probably in the second half of the next year.
Thank you,
and
Stefano.
also to know about future common projects and future achievements.
In fact, the behind the scene we were talking about, we have an IVS conference, an Israeli conference that we organize every year from the Israeli Vacuum Society, and we had the commitment from the embassy to sponsor 4 or 5 scientists to come. I was really counting on this, and then of course this is not going to happen this year, but Stefano, I hope we have a rain check for next year.
Yes, sure. We keep the money apart from this initiative. Sure.
Fantastic. So thank you, everybody. Thank you for the patience. Again, I'll tell you that I have been glued to this screen for the past whatever amount of hours from the beginning, which is very unusual for me because I think I'm an undiagnosed case of ADHD. But so they were so fascinating that it was really great. So thank you to all. And please, 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 you know the email of each other. With Google today, we can find everybody else. So let's keep in touch and let's contact each other and let's see. I hope that we can do a conference like this in a year and then say, okay, we start first with an outline of, okay, these were the grants we obtained, these were the collaboration projects we started with, these were the papers we published, and we can claim that this was really, really a success. At least so far it is in terms of attendees and in terms of speeches. Let's hope in terms of, like we say here in Israel, tachlis, the concrete goals achieved that we can do. So thank you to all. Thank you very much.
Goodbye.
Thank you.
Thank you.
Goodbye.
Bye.
Bye-bye.
Bye bye.
Thank you.
Bye-bye.
Bye bye. Thank you.